Hello, we will continue solving the last examples using the slope deflection method. Now in that example, again, I have this beam, I have a support here. And here in this support, we don't have any loading, but we'll have a support settlement. Now we will try to see what will happen if this support moves by 1 centimeters or 10 centimeters in the downward direction. Settlement of 0.1 meters. Okay, so this support moves due to some reason, weak foundation, and we see 10 centimeters in the movement in the downward direction. And let's calculate what happens to our structure. This length is 6 meters, this length is 4 meters. This is point A, point B, and point C. Okay, now let's first do the discretization. Node A, member AB, node B, member BC, and node C. The degrees of freedoms. So here we have a rotational degrees of freedom. I'll call it theta B. At the same time, we say that, okay, there's support. We say that there is no translation in the vertical direction. But we know that there's a translation, right? It happened because we don't have a strong foundation. But the difference is there's delta B, and we know its magnitude. Delta B is equal to 0.1 meters. So what I'm doing here is I'm considering support settlement as a known degrees of freedom. Okay, now the rest is the same. Let's again draw the free body diagram. I don't have any loading, but there's a movement in the support, and because of this movement we will see some moments. I have a MAB here, MBA here, MBC here, and MCB here. Okay, now remember that this is a 1 degree of freedom system, and we have only one unknown, which is the rotation at B. So I will need a moment equilibrium at node B. So sum of moments at B must be equal to 0. So this tells me that MBA plus MBC must be equal to 0. Okay, now let's write the slope deflection equations. So for member AB, it was initially straight, but it moved in the downward direction. Magnitude is 0.1 meters. That's our phi angle. Phi is in the clockwise direction. Let's say that is A and B. So phi is equal to minus, because this is clockwise, 0.1 divided by 6, or in other words it's minus 1 over 60 is the phi angle. So moment BA will be then equal to 2EI over 6, theta A is equal to 0. I got 2 theta B minus 3 times minus 1 over 60. And there's no fixed end moment. So the result is 2EI over 3 theta B plus 3EI over 60. Over 60, you divide it by 3, this should be, sorry, EI over 60. This is 1, this is 3, 3's will cancel and I got EI over 60. Let's take a look at member BC. So it's initially like that. Point B moved in the downward direction by 0.1 meters. That's B, that's C. That's our phi angle, chord rotation. Now the chord rotation is in counterclockwise direction. So phi is equal to 0.1 over 4. In other words, it's 1 over 40. Then MBC is equal to 2EI over 4 to theta B minus 3 times 1 over 40. This is 1, this is 2, and the result, the equation is EI times theta B minus 3EI over 80. Okay, so these are the two equations. Now we can write down the equilibrium equations. We already write it here. Sum of moments at B must be equal to 0. So MBA plus MBC must be equal to 0. This gives me, 5EI over 3 theta B minus 5EI over 240 must be equal to 0, and from that we obtain theta B as equal to 1 over 80 radians. Okay, that's the rotation. Now put this rotation into these two equations and calculate the member and forces. And when you do that, you obtain MBA as equal to EI over 40 and MBC as equal to minus EI over 40. If you calculate MAB, we don't have the equation, but you can just derive it from the slope deflection equations. MAB will be equal to 5EI over 240 and MCB is equal to minus 5EI over 160. And let's draw the free body diagram one more time. So at A, I got a counterclockwise moment. Magnitude is 5EI over 240. And a counterclockwise moment at B, that's EI over 40. Now at B, we see a clockwise moment, again EI over 40. And another clockwise moment whose magnitude is 5EI over 160. Now let's draw the moment diagram. The sign convention is as follows. And the moment diagram for this member, point A, I have point B here and point C. So at this point I have a negative moment, magnitude is 5 EI over 240. At the end of member AB, a positive moment, magnitude is EI over 40. And at point C I have another negative moment, magnitude is 5 EI over 160, and the variation in between is linear. So that's the moment diagram, minus, plus, and minus. So as you see, when we have a support displacement, support rotation, we can have any kind of movement in the support. The only thing that we need to do is to consider it as a known degrees of freedom. Once you do that, the rest is just the classical slope deflection solution. In this example problem, we have a frame composed of 3 columns. I have a fixed support here, another fixed support, and here we have a pin support. And I have a uniform distributed load on this member. 18 kilonewton per meter is the magnitude of the uniform distributed load. So this distance is 6 meters. That distance is again 6 meters. The height of the first column is 3 meters, and this one is also 3 meters. Let's label A, B, C, D, E, and F. Let's try to analyze that structure. Okay, I will just calculate the unknown degrees of freedoms and stop. Now the thing that we have to first check, now as you can see, we have a symmetrical structure here. These 2 columns are identical, the beams are identical, and I have a column at the middle. I have to mention that this frame is axially rigid. Okay, so what do I know about this structure? So there's this part is the symmetry axis, and since we have a symmetry axis here, symmetric structure, only we have a vertical load. I know that there's no translation. That's something I know. Delta is equal to 0. That's the first thing. The other thing is, if this is symmetrical, then the deformation on this side and on this side must be equal to each other. So this is the way the columns look. This is axially rigid. It won't move in the up or down direction. And whatever I see on this side, I should see the same thing on the other side. So that's the expected deformed shape of the structure. So things I know, this rotation and that rotation, magnitude wise must be equal to each other, but they should be in the opposite direction. And also I must have a 0 rotation at this end. Okay, so let's sketch the deformed shape before we jump into the solution. So we expect to see a deformed shape as follows: 0 translation, that's 90 degrees. So 0 rotation here, and that's it. So things we know. We know that due to symmetry, we can say that delta B must be equal to 0. No translation. What else? Theta B must be equal to minus theta E, right? because of this given deformed shape. And the other thing that I know about this structure is delta C must be equal to 0. Now at this point I started to think, what is the best way, what is the simplest way of solving this or analyzing this structure is for me is to generate the equivalent structure that will give me the same deformed shape. Okay, so I'm just divide this structure from the symmetry axis. So I did that, I'm doing it. Okay, I divide this structure from the symmetry axis, and then whatever I have as the boundary condition, put it in here. Rotation is equal to 0, right? And also the vertical translation and the horizontal translation, they should be all equal to 0. So which actually is the definition of a fixed support. And on this side, I have a uniform distributed load that's equal to 18 kilonewton meter here. So what I did here is I just take a look at the way the structure deforms, right? Since it's symmetrical, the loading is symmetric, it's easy to sketch it, right? And since it's symmetrical, we can write some relationships between the degrees of freedom, and we can say that certain degrees of freedom should be equal to 0. So doing that helped me to reduce the number of unknown degrees of freedoms, plus helped me to simplify this structure. And my assumption is these two should give the same deformation, same forces on the members. Now, let's do the discretization now. That's node B, member BC, node C, member BA, and node A. And I have a uniform. Oops, we don't show it in here. Sorry for that. Okay. Now the degrees of freedoms. We got only rotation at B. So I got 1 degrees of freedom in this equivalent structure. If without using this, without checking the deformed shape of the structure, if we just want to jump into the solution, we would have 1, 2, 3, and 4 degrees of freedoms, which would give us the correct result, but it's a long solution. Okay, so we said that we got 1 degrees of freedom. Let's draw the free body diagram. Uniform distributed load here. I got MBA, MBC. Sorry, this should be rewrite everything one more time. This is MBC, this is MCB. I got MBA here and MAB here. And the equilibrium equation is sum of moments at B must be equal to 0. This tells me that MBA plus MBC must be equal to 0. Now I will write the slope deflection equations. So for member BC, it is 2EI over 6 2 theta B, theta C is equal to 0, translation the phi angle is equal to 0, plus 18 times 6 squared divided by 12. From that, I obtain MBC as equal to 2EI over 3 theta B plus 54. Now let's write what MBA is. MBA is equal to 2ei over 6. Again, I got 2 theta b. So that's equal to 2ei over 3 theta b. Now, equilibrium equations. MBA plus MBC is equal to 0. This tells me that 4ei over 3 theta b must be equal to minus 54, and from that we obtain theta b as equal to minus 40.5 divided by ei, and that's the value of the rotation. And let's show it on the deformed shape. This rotation, it's in the clockwise direction, right? It's equal to 40.5 over ei, and this rotation here is in the counterclockwise direction, but it has the same magnitude, 40.5 over ei. Okay, if you have any doubts about these relationships, use all the degrees of freedoms and solve it. If not, if you are sure that the structure will deform in the following way, and you have these following relationships, and you will have a very simplified solution.